Alright, welcome to the Lab 1 demonstration. So purpose of this lab was to model an object moving at constant velocity. First part of the lab involved us filming an object and plotting its position versus time using the tracker software. The second part had us using VPython coding to create a graphic of an object moving at constant velocity and plotting its position versus time as well. And we're going to be comparing those plots soon. Concepts used in this lab, so the main concept is Newton's second law, which is that force is equal to mass times acceleration. And this means that if an object has an acceleration, then there must be a force acting on it. And formulas that we derived are final velocity is equal to initial velocity plus F net over mass times delta t. The F net over mass was derived from the F equals ma up here. And the second formula is final position is equal to initial position plus V average times delta t. And as our lab focused on constant velocity, this meant that the average velocity is equal to initial, which is equal to final. And here we'll get into the tracker demonstration. So I have the coordinate axis set up right here, hugging the left side of the wall and going in the positive x direction. And right here we're going to play the ball coming through. And we start plotting the points as the ball moves in the positive x direction. And you can see it plotting its graph up here and all the chart with the positions down here. You can see the initial time, 0.666, and the initial position. And that'll be the end of that, and we'll move on to the calculations. So the calculations, I show that we were able to get the position and the velocity we got from getting the distance that the ball traveled in 0.033 seconds and dividing by 0.033. So that gave us 0.522 meters per second. And since F net is 0, that means that this 0.522 is the average velocity throughout the entire experiment. And here we're going to walk through the code. So the main changes I made was, one of them was the ball mass. Since it is a bouncy ball about 2 inches in diameter, we kept that accurate. We have the initial position right here and the initial velocity as well, which we got from the tracker, and the initial time also from tracker, and the time step, which is 0.033. And then right here we have the we don't want the time to go above 1.7, keeping the size of the plots roughly the same between tracker and this one, making sure the F net vector is 0, and then adding in the velocity formula, which is final is equal to initial plus F net divided by the mass times delta t, and the position equation as well, which is final equals initial plus velocity times delta t. And now we're going to run this code, and as you can see, the ball moves, and it starts off at the initial position and time as was mentioned earlier, and it goes in a smooth upward slope. And we're going to compare the two plots right now. So the blue line represents the theoretical, and the red line represents the experimental. Experimental is tracker, theoretical is Python or coding. And you can see the slight difference in the graphs. It gets more apparent towards the end, and we're going to go into why they actually are not the same right here. So source of error was one of the assumptions we had about this experiment was that there was no net force acting on the ball at all. However, this is not the case, as there is still friction and air resistance as the ball rolled along the table, and this is more than likely the cause for the slight difference in our plots, and why the theoretical model was able to go further in the same amount of time. So in tracker, I had the coordinate system set up so that the ball was moving in the positive x direction, so that way when it would plot it, the data would be going in the positive y direction, and it would have a positive slope as time progressed. If we flip the plot over the x-axis, this would mean that the ball would be going in the negative x direction, and the data would have a negative slope, which can be shown right here. So the purple is the theoretical flipped, and the green is the experimental flipped. You can see that it's just flipped right over the x-axis, and this shows that the ball would have the same displacement, but it would move in a different direction. So they would both go away from the origin, go the same distance away from the origin, but in different directions. So this would be moving right if you take right to be positive, and this would be moving left. So what does this mean for the entire experiment? The net force of the theoretical model was set to 0, and it came quite close to the experimental model, but there are thousands of interactions in the universe, and it is impossible for us to add them up and get a net force of 0. We don't know which pushes are coming in and which pulls are coming in and how to combine them and balance them out so that the net force would be 0, and that way our experimental model would be closer to our theoretical.